All right, let's now take a look at the code example of VGG16 that I implemented here. I should mention that I don't want to rerun this here from scratch during this video, because it took 1.5 hours to train. It's a large network. So in that way, we will just take a look at the results. So I will, of course, share this with you. You should find the link under the video. So what we have here is all the usual imports, watermark, torch, torch vision, and so forth. Then my helper files, as usual, they are, I think, identical to what I used last week. I can't remember making a modification to them. So exactly the same like that we used for AlexNet. The only difference here is really that I have a different architecture. So defining our hyperparameter settings, random seed shouldn't be a hyperparameter, but you have to set it to some things. I'm setting it to 1 to 3, batch size to 256, and we're training for 50 epochs. And I was using a GPU for that because otherwise it took too long. So you could, for instance, run this on Google Colab on the GPU. If you run things on the GPU, this function doesn't really work that well anymore, because I actually cut this from the videos because it was too long. But just to briefly mention why. So when you train things on the GPU, there are different types of algorithms used for convolutions. So there's, of course, the convolution that we talked about in the lecture, but in code, people don't implement it this way. There are usually more efficient approximations of that, like a fast Fourier transform based ones. And depending on what computer you use and what graphics card you use, different approximation algorithms are used. Although these approximations are pretty good, they are approximating the convolution very, very well. There are tiny differences after the decimal point, and if you have a lot of tiny differences, they can add up, and then sometimes you will find that results are different when you run them again, because not only are different algorithms automatically chosen based on the computer, but also when you run it multiple times. So NVIDIA is actually running some automatic way to guess which algorithm might be a good choice at a given time. So that is why there are sometimes slight differences. It used to that you could set this to a deterministic setting, but for some reason it complains now that this deterministic setting doesn't really work anymore. But in any case, you don't have to worry about that. It's very normal in deep learning that you get different results if you run things again. I mean, they will be slightly different. They will not be very different. It's just like very, very small differences. Any case, let's not worry about this. Okay, so talking about the data set now. So here we're working with a Cypher10 data set, which is 32 by 32. But yeah, I resized this because VGG, if you look at this figure again, it was originally developed for 224 times 224 inputs. And there are just too many layers for small inputs, because you halve the size of the layers, and it's at that point, if you have half the input size, you will already have only 3 by 3 or 4 by 4 layers here. And if you make it even smaller, it would be 1 by 1, or even smaller if you have here already 1 by 1 and then try to halve it. So that way, we can't have inputs that are too small. It actually works with 32 by 32, but the results were not as good. So it was faster, of course, but with this version where I slightly upscale, I get actually 85% accuracy. So what I'm doing here is I'm upscaling these images from 32 to 7070. Then I do a slight random crop here. So the random crop is to avoid overfitting, or not avoid overfitting, but to reduce the overfitting, to make it a little bit less sensible or sensitive to exact pixel locations. And then I'm converting it to a tensor and then normalizing it so that the pixels will be centered at 0 across the channels and have a standard deviation of 1. So it's the usual procedure. Again, for testing, I don't do any random crop, I'm center cropping. And then the rest is exactly the same that we talked about for AlexNet last week. So here's the interesting part, that's the VGG16 architecture. I just had some notes for myself for calculating the padding, but we probably don't need that here. So how I implemented it is in different blocks. So I have one block that is usually the convolutions, and then the final layer in that block is the max pooling layer that reduces the size by half. So These preserve the size. It's the same convolution with the padding such that the input equals the output size, and max pooling reduces the size. And then again here, this conserves the size, this reduces the size by half because of the stride. Then here again we have another block with max pooling, another block and max pooling, and another block and max pooling. And then these are what I call my feature extractor layers. And then we have a classifier layer. This is really, if I go back to the figure, this is really this last part here in light blue. This is the fully connected part. So here a linear layer, a fully connected layer, essentially, another one and another one. So you have dropout. I should probably, this is a 1D dropout version. So if you want to add dropout for other layers, you have to, I would recommend using dropout 2D. Actually, I recall I forgot about that recently, and I used a regular dropout somewhere because I, for some reason, forgot to type 2D, and I was wondering why I couldn't notice any difference. All right, here I'm using the K-Ming uniform weights as given here because that's what was used in the original paper. Then I have an adaptive average pooling, which will, in this case, make things equal to the height and width here, so that I chose to be 3 by 3. So because for the linear layer you have to know the input height and width, because you need to know the number of features. We always know the number of channels, right? Because it's coming from here, but sometimes it's hard to know what's the width and height to compute the number of features. So usually what we do is we have here the feature map and then average pooling, and then what we do is we flatten. This is essentially a flattening operation. This is essentially the same that you do when you work with multi-layer perceptrons and MNIST. So you basically flatten the input, which is a image. You flatten this to be a long vector. That's the same operation here. And for that, you have to know the number of parameters because you need to know the number of weights, right, for the multi-layer perceptron layer, the linear layer. So how would you get this information? Here I'm using adaptive average pooling. So adaptive average pooling is an operation where you can determine the input and output size, and it will either add the strides or the padding such that this dimension will be met. So if the input is, where am I here? If the input to this one is smaller than 3 by 3, it will add padding. If it's larger than 3 by 3, it will not add padding and do some strides to reach that size that we desire. And if you don't want to do adaptive average pooling and you want to know the number of sizes that come out of the last block, for example, one way would of course be to use the equation that I showed you and just calculate it by hand. That is a valid approach. That could be a potential exam question, but we don't have an exam anymore, so don't worry about it. Maybe something for the quiz. But in practice, people would write forward or backward hooks. I think I explained it, so you would use a forward hook here. I explained it to you when we talked about the PyTorch API, but to be honest, even that is something most people won't do because it's just too much work to write a hook function. I mean, I wouldn't do it. The simple brute force way would be to just implement a print statement temporarily. So what you would do is you would just have something, it's the lazy but efficient way, something like x.size. It prints the size here of x. Then you would run this here. When you do the training, it will output the size. It will probably crash if you don't have the right dimensions, but then you know the size, right? You know the height and width then, and then you can remove it, add the desired height and width here, and you're good to go. So in practice, most people, to be honest, are just inserting, if you want to know the size, you just import a print statement, and that's how you find out the brute force way. Okay, so this is essentially the VGG architecture. So you can see there are essentially convolution layers, followed always by max pooling that halves the input size. We have many of those. Then these classification layers here. And then we have here the training, so I'm initializing it for 10 classes. If we look back to the slides, it's 1000 because ImageNet, the dataset that they used here, had 1000 classes. We have Cypher 10 with 10 classes only. I use SGD with Momentum, and this learning rate scheduler that reduces the learning rate by a factor of 10, so dividing it by 10 if the validation accuracy doesn't improve. So this is just my training script that I used for AlexNet 2. Alright, so here's then the training, the same as with AlexNet. You can see it trains pretty quickly, 35%, 50%, 53% accuracy, so it's slowly climbing up. At some point it stops around here, it's improving a little bit, but it takes longer, more epochs. So I do that. So it's sometimes, it's very useful to look at this. If you run an expensive network like VGG, it might be taking a few hours, and you probably want to take a look at the beginning whether it's even worthwhile training it for 50 epochs, right? So if you notice that the loss doesn't go down, maybe in the first 4 epochs or something like that, or you notice the accuracy doesn't improve, then I would just stop the training and maybe change some parameters before you just waste 1.5 hours waiting until it finishes. So this is why I'm printing this during the training. There's a tool called TensorBoard that can create visualizations during training. We are not talking about this in this class because I think we already have enough tools for you to learn about, so there's already enough code going on, but you're very welcome to check this out at some point. It's also nice for visualizing things. But here I'm trying to keep things simple, so not too many tools at once. It's already enough you have to learn in a way. But at the end, I always find it still helpful to take a look at visualizations. Here I make them, of course, with Matplotlib, so that you can't see them during training, only after training. But what you can see is the loss goes down pretty nicely, so it kind of converges here after 50 epochs. Maybe it would still improve a little bit, but looking at the validation performance here, so in orange, you can see maybe it would go up slightly more, but you can already see after epoch 10 there's a huge amount of overfitting. So to reduce that overfitting, maybe adding some dropout 2D might help. You can actually, that's maybe a good exercise, you can actually insert a regular dropout, and you will see with a regular dropout that you won't reduce overfitting too much, but if you use dropout 2D, that helps actually more with convolutional networks. Okay, so this is that, and then here just the visualization, looking at some examples. You can see most of that looks correct, so P is predicted, T is the true label. You can see this one is wrong, deer and frog. It's hard to tell. I mean, if you look at this, Cypher 10 has such a low resolution that even we have difficulties telling what's in these images, I think. All right, so here's a confusion matrix. So that looks actually interesting. You can see dog and cat are often misclassified here. And that is kind of reasonable because cats and dogs are both animals. So a cat and a dog are, for example, very different from an airplane. So dog and airplane is rarely confused, whereas dog and cat is more often confused. In the grand scheme of things, that's kind of reasonable, I would say. So you can actually see all the animals. That's very interesting. So you can see all the animals here in this square often misclassified compared to ships and trucks and like automobiles. So here you have things, and then you have the animals. Animals among each other are harder to classify compared to other objects like airplanes and automobiles. All right, so this is VGG16. Maybe one more thing, I have VGG16 standardized. I was just toying around with it to see if proper standardization can improve things, but it didn't turn out to be true. So just to show you the, I would say, proper way. So scrolling up again, here I'm just using 0.5, 0.5, 0.5, which will scale the pixels such that they are between -1 and 1, centered at 0. So using 0.5, but we can actually use the proper standard deviation and feature pixel mean by computing them. So here I just have a function added to it that computes or approximates, actually, because it's faster, it approximates the mean and standard deviation for each channel, for each color channel. That's the red, green, and blue one. So they are around 0.5, and then here the standard deviations, they are 0.25 instead of 0.5 in what I assumed in the previous code. But if I use these proper ones, instead of just using 0.5, I find that it doesn't really make any difference in all. So the performance, I think, was pretty much the same. Actually worse, 82. Oh, actually it's an interesting drop here. It's probably due to overfitting, more overfitting. Yeah, so, but you can see in this case I didn't gain anything from doing this other standardization. Maybe it's actually training better, though. You can see it's dropping more here. Could be because the scheduler is triggered at that point. It doesn't have to be because of choosing the mean and standard deviation, could be just coincidence. All right, so that was a long video probably, so let me wrap this up. In the next video we will talk about residual networks, which are a little bit more interesting than just adding more layers to it.